So in this lecture, I will walk through the problems that were assigned from chapter 6. So there were 18 problems in total that were given throughout the chapter's material. And hopefully this table here, 6.1, looks familiar. We're going to reference this regarding to which bonds we will be breaking and which bonds will be forming in some of these problems. So we'll come back to this table as needed. Let's start with our first practice problem here. So we see in reaction A that we have a hydrocarbon, right? So we can draw this out like CH3. We have two hydrogens in the middle here, and then we also have a CH3 here, and then we have our bromine-bromine bond. So when we go to our table, specifically, we're going to be looking for this bond here that's breaking and this bond here that's breaking. So let's take a look and see what that would look like on our table. So we have a CH bond breaking in a propane. So that will be this value here. So the way that you could look at this molecule is that there's a carbon that's bonded to two hydrogens, and it's also bonded to two methyl groups, right? So CH3, CH3, and then the two hydrogens. So this is the value that we're going to use for our CH bond that's breaking. And then our bromine-bromine bond will be down here. That will be 193. So let's go write these values down here. So we have to put in positive 397 to break that bond, and we have to put in positive 193 kilojoules per mole to break that bond. All right, so now we have our bonds that are broken. Let's look at our bonds that are formed. So we have here the carbon-bromine bond, and then we have HBr. So this is our other bond that's formed. So let's go back to our table. Here, let's make a list. So our CBr bond, and then we have our HBr bond that we're looking for as well. So on our table, they will look like this. So we have this molecule over here. If we were to expand it, again, we have a carbon in the middle that's bonded to H and Br, and then that same carbon is bonded to two methyl groups, right? So this is the bond that we're looking at here, that's CBr, and that's highlighted in red. That would be 285 kilojoules per mole. And our second bond that is formed is HBr, so that's down here. So that would be 368 kilojoules per mole. All right, so let's go back and figure out what we're going to do with these numbers. So we know that this was negative 285, right? This is how much energy is released when that carbon-bromine forms. And then when our hydrogen-bromine bond forms, we're going to release 368. All right, so now the general form for this type of problem is that we add together 397 plus 193, and then we're going to subtract the sum of 285 and 368. So we find the difference between these values is negative 63 kilojoules per mole. So for reaction A, we would make a determination that this reaction would be considered exothermic. Let's take a look at reaction B here, right? So how do we find which bonds are being broken, which bonds are being formed? So it looks like we have our molecule here, which has chlorine on it. And then over here, now it has an OH group. So this bond here must be broken. And then we have HOH here. So one of these OH bonds will be broken as well. And our bonds that form, we're going to have this OH bond, so a CO bond rather, will form over here. And then we have HCl, so an HCl bond will form. All right, so let's go to our table and see if we can figure out the two bonds that will be broken, what those bond dissociation energy values would be. So here's our table. So again, we have a carbon in the middle, but now it's going to be bonded to three CH3 groups and that chlorine. So let's see, what would that look like? So we have something over here that we're looking for, right? So our carbon halogen bond is the one that will be broken, but we need to look at a carbon that's bonded to three methyl groups specifically. And we would find that that requires 331 kilojoules per mole, so positive 331 for this reaction. And then our water molecule, let's see, where is that? HOH, that is given down here. So right here, this 498, that will be our other positive value. So these are the two values that we'll use for our bonds that are broken. So let's go and we'll start writing them down. So we have 331 plus 498. So this is the energy required to put into this reaction to break those bonds. And then, oh, let's go back to our table again, and we're going to look for this CO bond and then this HCl bond. So when bonds form, right, energy is released. So we'll locate our same molecule here, but now with a COH bond, right? Carbon bonded to this hydroxide group. So we have a release of 381. Oops, so I'm sorry, this would be negative 381. And then we have for our other bond that's formed, that would be our HCl, and that's over here. So we have 431. So negative 431. So let's go back to our calculation. We'll add these values together, right? So minus, we had 381 plus 431. So overall, after we find the sum of these two values, the energy that we have to put in, and then we subtract the sum of the values of energy that's released when the bonds form, we see that overall this turns out to be a positive 17 kilojoules per mole for this reaction. And this reaction we would say is then endothermic. So for the remaining two reactions, you would do the same thing. You would find the bond dissociation energy. All of our starting materials for the next two are very similar. So you would go to the table in the same area, right? And we would just change our values from 331 to 272 for our bromine here, and then 209 for our iodine. But it's the same value for water, for that HO bond that breaks, so 498 would be used. And then our products would have very similar energies again, but instead of HCl, we would use the values that are hidden under here for HBr 368 and HI 297 in questions C and D respectively. All right, so that's everything for problem 1. We'll continue next time with example number 2.